Okay, so now we're going to look at the proof of Theorem 10, the chain rule. So the proof is going to involve lemma 1 that we just proved. So proof. So note, we're looking at dz dt, so derivative of z with respect to t. So by definition, that's going to be d dt of my f function. Then we're just going to write the definition of derivative below here. So definition of derivative, math 150, limit h goes to 0, going to be f of x t plus h y t plus h minus f of xt yt all over h. Okay, so that's the definition of derivative. Now we're going to do a little trick here. So the trick is, so note, say a minus a is 0. So I can add and subtract the same thing in this fraction, and it'll be 0 like this. So I'm going to choose to, you'll see here, I'm going to write this as, so the first one will be the same, x of t plus h, y of t plus h. Now I'm going to try, my a value I'm going to put here is going to be f of x t plus h, x of t plus h, y of t, and that'll be that guy, and then plus, I'm going to add that one in, f of x t plus h, y of t, and minus f of xt yt, all divided by h. So this is like my a here, or my minus a, and this is my plus a here. So we just added and subtracted a, this whole thing's a minus a. So I'm going to break this now into two fractions. So the limit h goes to 0. It's going to group the first two. It's going to be f of x t plus h, y t plus h, minus f of x t plus h, y of t. This can be divided by h. Then I'm going to do the limit of the last two guys here to be plus. So I'm distributing the limit. So the limit then, h goes to 0, these two, divided by h. Then I'm going to apply the lemma we just proved. This guy, x of t, y of t, divided by h. Okay, I'm going to apply lemma 1 now to the top parts of these fractions. I'm going to apply lemma 1 here, and apply lemma 1 here. Apply lemma 1 here. For both of those guys. Let me move this over a bit here. So applying lemma 1 then, so that's that. So looking at lemma 1 then, this is going to become the, well here the y's are changing, x over the same, it's going to be partial y. That's going to be x of t plus h, then y tilde times y t plus h minus yt. And the h value at the bottom here, I'm going to put at the bottom of this one. Then plus, applying lemma 1 to this guy now, the x's are changing, y's are the same, it's going to be partial with respect to x, going to be x tilde then y of t times x t plus h minus x of t. And again, the t value, sorry, the h value I'm going to put here. Oh, I guess I forgot my limits here in front of all these. Give you a limit for this one. Limit h goes to 0 for that one, and plus limit h goes to 0 for this one. Then off the side here, let's note that, so the way, so x tilde goes to xt, and y tilde goes to yt as h goes to 0. So let you think about why that should be the case. Okay, well, the reason is because x tilde is between, look back at the proof of lemma 1, x tilde was between xt and xt plus h, but if h goes to 0, then it's going to be forced to go to xt. Same for y tilde. So therefore, and also looking at this, that's the definition of derivative dy dt. So that's going to be dy dt, that limit. And this guy here, if I take a limit h goes to 0, that's going to be dx dt. So we'll get then equals, so it'll be just fy xt yt times dy dt plus here partial derivative with respect to x, xt, yt times dx dt. And that's what we're trying to show. That's the chain rule. So hence, claim follows. Claim follows. So we're done. Good.